In this lecture, we're going to talk about the topics on the summing amplifier, both inverting and non-inverting, and also the buffer or a voltage follower. So the first example is for the inverting topology. So you can use the inverting topology to add different voltages at input to the output. So the structure looks like this. Okay. You have three input voltages, V1, V2, V3, being shorted to the inverting terminal through all these three different resistors. And here's a feedback resistor, here's VO. And this is ground, 0 volts, ground. So here's the virtual ground. Virtual GND. So VP and VM are virtually shorted. Okay, keep in mind. The purpose of the calculation is to get the voltage gain of VO over VIN. Since you have three different VINs, so I have to add all the three currents to the same joint, which is here. So I have one current contribution, another one, and the third one. Because this is 0 volts virtually, so the equation should be V1 minus 0 over R1 plus V2 minus 0 over R2 plus V3 minus 0 over R3 equals to what? Equals to 0 minus VO over RF. All right. So it's hard to get one clean conclusion from this. So if we assume R1 equals to R2 equals to R3 equals to R, then what's going to happen is we're going to have V1 over R, or if you can expand it, plus V2 plus V3, because they are all R's at the denominator here. And this will be minus V over RF. So VO over V1 plus V2 plus V3 will be the voltage gain, which is RF over R. So that's the voltage gain for the summing amplifier using the inverting topology. So you can see that the inputs are being added up as one input for the circuit. And here's the voltage gain. So next, we're going to look at the non-inverting topology for the summing amplifier. So we need a superposition to solve this type of circuit over here. Let's take a look at this. Minus plus, here, feedback. So RF, VO, I'm going to name this at R3 because I have two resistors here. This is R1, which has a V1, and R2, V2. They're both contributing to the non-inverting terminal. And because we know this is VO, and we call this VP because this is V plus, this is V minus. So what we can get here is, since we know VP equals to VM, according to the non-inverting amplifier's voltage equation, we know that VO equals to VP times 1 plus RF over R3. You know, just use the equation we got in the last lecture. So now here's the equation. Here's the question. So what is VP? If we know VP, we just plug in. We directly know the relationship between VO and V1, V2. So we should find out the relationship between VP and V1 and V2, right? So this looks like a DC circuit. We can get equivalent version. For example, That's I'm missing a resistor here. That's R1, that's V1, and then R2, V2, and they are both grounded because the voltages are grounded. So see V1, V1, R1, R1, V2, V2, R2, R2, and they are being shorted to one terminal, which is here, and this is VP. We're just trying to calculate VP. Since you have two voltage sources are contributing to the same voltage, so the best way to solve it, you can use many different ways. For example, you can get a KVL, no problem. But I'm trying to use superposition, which we just learned. Trying to let you know how you can do it in real life using superposition. So first, the step one, okay, V1 only. Then what's going to happen? So we are going to short this voltage source, and we only have V1 with one resistor, another resistor, R1, R2, and here's VP. So VP will be V1 times R2 over R1 plus R2, according to the voltage divider theory, right? So what about the second version? If we have V2 only, then this one should be shorted, but only V2 being used. R2, R1, and here is VP. So VP will be V2 R1, R1 plus R2, right? So we are getting two VPs. We're getting two VPs. According to the superposition theory, so the overall VP equals to V1, the two VPs being added together. So V1 R2 R1 plus R2 plus V2 R1 R1 plus R2. It's hard to get a clean result, as well here. So we are going to assume R1 equals to R2 equals to R. Then what's going to happen is VP equals to V1 plus V2 like this. And then we're getting V1 plus V2 over 2. Okay. Then we plug this back in here. So we are getting VO equals to V1 plus V2 over 2 and 1 times 1 plus RF over R3. And then VO over V1 plus V2 equals to 1 plus RF over R3 times a half. So that will be the overall voltage gain for the summing amplifier using a non-inverting op-amp. Okay, so these are the two summing circuits I will introduce to you in this lecture. And now the last one I'm going to introduce to you is the buffer. It's called a buffer or voltage follower. It's being used a lot in circuits. It's very useful. So the topology looks like this. Minus plus, here's VI or VIN, that's ground, that's a power, that's VO. So here's a question, right? So here's the inverting terminal. So because we are using a buffer and voltage follower or any other types of amplifiers or closed loop amplifiers, we need a feedback loop, right? Always use a feedback loop. And the feedback has to be negative feedback. So which means you have to short the inverting terminal to the output to form a circuit. I mean, if you're shorting the non-inverting terminal to the output, the situation is just getting worse. It's not trying to make these two terminals being to be close to each other. It's just making the difference bigger. So you have to use negative feedback. So whenever somebody is asking you why the inverting or non-inverting amplifier has the VM and VP to be equal to each other, so the answer is negative feedback. Because of the negative feedback, it's always making these two terminals being close and close to each other from the effect of the infinite open loop gain of the op-amps. If you forgot why, I mean, look at the previous lecture, the very last lecture, so you can see the explanation over there. So for this one, there's no voltage gain, doesn't like the inverting topology. There will be a gain because you have these two resistors can give you a different design or customized ratio for the voltage. So for example, this is a very typical inverting topology for the to amplify a signal. So V over V in is definitely minus RF over R1 very easily. But now here is also a negative feedback. Negative feedback. There's no resistors over here. So the gain will be 1 because there's nothing. It's just the same resistance here and here. So the gain will be 1. So Vi equals to Vo. Okay. So the application of this type of circuit is really broad. I mean, I just list 2 of them for here. So it's used as a buffer to boost the driving capacity or capability of the circuit. To boost the driving Why? This can increase the driving capability of the circuit because you can see that even though the voltage is being delivered to here is the same voltage, but this guy has an independent power supply. So it's going to drive, charge, and discharge the voltage back and forth over here. So we can have a little bit larger load to be driven by the same voltage. Okay, and the second application is to isolate the input and output. Why I want to do that? Because in a lot of cases, here V in may have a resistor network, right, like this, and it's providing the voltage to V in. However, if something of a resistance load is being shorted to the output, you can see that if you do not have something to isolate these two terminals, you are going to have this one directly being shorted to this resistor. What you are going to get will be this. So you can imagine that the voltage will be shared or will be dropped from the input voltage here because you have a parallel resistor here and they have pretty much comparable resistance values. So the whatever voltage here is trying to be delivered 100% will be compromised because it's being dropped here as well. However, you have something to insulate the two, to isolate the two output and input, then this won't happen because this guy has ideally has output voltage to be 0, so nothing will be dropped inside the op-amp. So everything will be delivered. Pretty much everything will be delivered output. It's another benefit by using the buffer or voltage follower in the circuit. All right, this is everything I'm going to cover in this lecture. I'm going to see you in the next video.